So I think we're going to go ahead and get started. Yeah, my clock is counting down. So my name is Eric Cheddar. I'm joined here by Lee Rhodes, and we'd also like to do a big shout out to someone. We both work at Yahoo. We'd like to do a big shout out to someone at Yahoo Labs named Kevin Lang, who has helped a lot with all of the content that we're going to talk about today. At Yahoo, I normally work on a distributed real-time system called Druid, but today I'm here to talk with you about summarization, approximation, and sampling. And this is basically a set of tools that we use inside of Yahoo to make large data sets more manageable. And a little bit of structure. I'm going to start out introducing summarization, what it is, why it's important, and at the end, there's going to be a problem left behind that Lee is going to come up and tell you about how we solve using approximation and sampling. Before all of that, some context around Yahoo. As you can probably imagine, and you might have heard at some point in time, we deal with lots of data. We have tens of billions of user events every day that come in from people using the Yahoo homepage, using Yahoo Sports, using Yahoo Finance, using Yahoo Mail, all of those various things. There's many complex interactions, various things that they do on various parts of the site, and in order to understand all of this, we need to be able to really understand their activity, the activity of users in individual groups as well as a whole. And we need to be able to slice and dice that by various dimensions. What segment, demographic segments, ad targeting segments, simple things like what device are they using to talk to the website, and various things like that. You can see a whole plethora of them up there. But this is the basic problem. When you have lots of data and you want to understand all of this, how do you do it? And how do you do it fast and in a quick iterative cycle? And the first tool that we use for that is summarization. So what is summarization? To define what summarization is, I'm going to start by showing you kind of what our data looks like and some of the questions we might ask about it. So this is some made-up data, as you can imagine. We have a timestamp column, a domain column. This would be the domain that a user visited, maybe. The user, so the ID of the user, what gender that user happens to be, and whether or not they clicked on an ad. Some questions we might ask about this data is like, how many impressions happened on each domain? Which domains are the top? Which are the lowest? Do we have more females than males, more males than females? What's the demographic breakdown of a specific domain? Or even, on this domain, how many unique female users were there? And these are all very interesting questions for ad targeting, for understanding who your users are, for understanding who's getting value out of your website. And in order to answer these questions, well, using this data, the way that we can answer them is, one, if we take the data and we assume each row is one impression, one ad impression, and each thing over here for clicks is one click, you can pretty easily summarize this and say what happened within the hour. And by just taking the first portion, the hour, and throwing away the rest. And we can do that and basically take this 10-row data set and turn it into just a single row. We had 10 impressions and 6 clicks. And that's pretty easy. It's generally straightforward. You add this up. You lose a little bit of fidelity, but hey, you can see your data at hourly granularity. However, it's lossy. We don't have a domain anymore. We don't have gender. We can't answer questions about user. We can't answer all of these individual questions. So what do? Well, we start reintroducing some dimensions. Let's say we reintroduce gender. For gender, we have 2 potential values, male, female. Technically, you could have other different values of gender, but for simplicity, 2 values of gender. And here we have our 10-row data set becoming a 2-row data set now with female and male. And we have our additions here. So now we can answer questions about specifically females or specifically males. We can also add up the values for these 2 rows and answer questions about the whole hour relatively simply. We can do the same thing for domain, where we have 2 domains, do the addition, and we once again have taken our 10-row data set and turned it into 2. This maps really well once you have billion and billion row data sets. It really shrinks things down. But with each of these, both domain and gender, what I've shown you, I can't answer questions about which gender visited which domain. And so for that, well, I add gender and domain into the same summarization here. And so here I can have Bieber.com and Ultra.com and female and male. And note, however, for domain, there were 2 potential values here. For gender, there were also 2 potential values. So you might have assumed that the output table would have been 4 rows, because 2 times 2 is 4. However, we actually only have 3 rows, because in my fake data set, females are the only gender that actually visited Bieber.com. And this sort of thing, this sort of sparseness happens a lot in real data, where you have, when you actually take the cardinalities of your columns and multiply them together, you get large numbers. But when you actually go and summarize, various combinations never actually appear. And so storing the summary actually ends up as a sparse representation of the actual input data, and it allows the data to shrink down even more, so this 10-row data set becomes a 3-row data set. And from here, I can answer questions about how many females visited Bieber.com, how many males visited Bieber.com, and the other way around. Now, the problem comes in when I want to reintroduce the user dimension. Now, if I want to reintroduce the user dimension, the big problem is that there was only 1 repetition here. There's only 1 user that did the same thing twice. And so if I try and summarize this down and keep that user column, I end up with a 9-row data set, because this row and this row are the only ones that get removed. And so it doesn't actually shrink the data down very much because of the uniqueness of this user value. However, if I want to answer questions about unique users, the traditional count distinct logic says that I must include this column, because you have to know which users were there in order to know how many of them happened. And so this actually produces a little bit of a problem that Lee will go into how we solve. But just to summarize summarization a little bit, it's this technique where you take your data, you throw away some columns, and do a little bit of an aggregation in order to shrink the amount of data that you're dealing with. There's a trade-off in fidelity. It's usually OK. For this example, I can't answer questions about what happened in a single minute. I can't answer questions about dimensions that aren't included in the summary. But there's usually some sort of 80-20 trade-off in your data, and it makes for much quicker processing times when actually answering these questions. Now, the thing that we were left with when using summarization is this: wouldn't it be great if we could have this exact same representation, have this 3-row representation, and still answer questions about unique users? Still know how many individual unique users came and visited, were females who visited Ultra.com or any other arbitrary combination. And for that, we found a solution. It's something called sketches, and it's an approximation, but I'm going to have Lee come up and talk to you about how that works.
Thank you, Eric, and welcome. So I'm going to address the problem of counting unique users in big data. It is a difficult problem, even from a computer science point of view. It hobbles many big data solutions, because computing unique users, trying to do traditional distinct counts with big data is painful computationally. So I'm going to put some criteria around how we want to answer this question in terms of the solution. We're looking for something that is certainly scalable, that can scale up to terabytes, petabytes in size, and not impose severe penalties in terms of computational cost. So we want something that is independent of the input data size. We're looking for the quality called additive. And what this means is we're used to adding integers and numbers together, and they add quite nicely and linearly, but unique counts don't. And they don't add because of the presence of duplicates. And so we need something that is not only small, but fast, potentially real time, and be able to eliminate duplicates. So there's this concept in streaming statistics called single pass or one touch. We want to be able to touch the incoming stream of data, whether it's from a big database or whether it's actually live off the wire, in one pass, one touch per item. We want to be able to also enable analysis over sets of users. We'd like to be able to say, oh, we have, say, a set of users from the US, a set of users from Europe. We'd like to know what users have checked into both European and US sites. So that's what we call set expressions. And certainly we want to be able to predict how well it's doing in terms of its accuracy in getting these estimates. The concept sketch, or the term sketch, it was actually coined by Andre Broder, and the beginnings of this science, of all the estimation and statistical sciences used in computer science, sketching is one of the newest and really didn't start to explode until around 2000 and 2002. It's a combination of theoretical mathematics and computer science, and sometimes it's given the word or the names stochastic streaming algorithms or approximate query processing. It basically is a data structure that's fairly small. We feed feed data into it, and one of the ways these sketches work is it makes the input data look like white noise. Gives us the property of white noise. Then it goes into this small data structure, and then you have an estimator at the end that queries this data structure and says, okay, what is your best estimate of the number of unique users that you've seen up to this point in the stream? So right away you get the idea these are approximate algorithms. But they're really more special than that. They're more special in the sense that they are approximate and you can actually qualify and predict what the error margin is. And we'll talk about that in a moment. So to get you comfortable with the concept of a way that statisticians think about making the estimate. So here you are, you're in a concert line, and you're on the left-hand side. You just joined the line, and you look down the line, you say, oh my gosh, how long am I going to have to wait? And how many people are in this line? So there you are, and there's the curb right behind you. It's 2 feet behind you. And so you know that you're in New York, and New York long blocks are a fifth of a mile. And that's why the cabs are rated in fifth of a mile chunks, if you didn't know that. And so you know this line goes down just the end of the block. So how many people is that? Well, a fifth of a mile is 1,056 feet. And so you can say, well, I'm 2 feet from the curb. Maybe everybody's spaced out 2 feet, so I divide 2 into 1056, and that gives me a sort of a guess. But the way the statistician would frame this, or the mathematician, he would say, well, I want a number 1 over d. So I make d equal to 2 over 1. He turns it upside down. D equals 2 over 1056, and that's about 0.2%. And then you divide that in, okay, say 1 over 0.2%, and that's the same, it's the same number, about 500 people. Well, that's a pretty poor estimate, because not everybody's spaced evenly. Some folks are far apart, they're dreaming, talking on their cell phone. Couples are standing closer together, holding hands maybe. So the spacing is quite random. But you look down that line, it looks sort of even. Well, that's sort of what we mean by uniform even, uniform random. So there's a little noise in their separations. So a better estimate though, since just taking one space, one little d there between 2 people can be pretty bad, you look down about 10 sidewalk cracks. And that's about 30 feet. So, well, how many people are in that space? And say, well, about 11 people. All right, so now I do another estimate with a little larger sample, so to speak, which is how far you can see into the line. And you say, oh, 30 feet, 1,056 feet, that's about 387 people. So that sample contains about 11. So that's what I'm trying to get you used to, is turning this number upside down of d of 1 over d or 11 over d, which is your sample size. Okay, so now we're going to build a real sketch. But here the problem is not just people aligned. We've got duplicates. We've got identical twins that you can't, you want to say, well, I just want one of the pair or whatever. So I have big data on the left, and I'm going to feed, what happened to my numbers here? Oh, I jumped ahead accidentally. Okay, so I've got big data on the left. I'm going to feed it through this function, which basically makes the data look like noise, which is like a random hash function. And all the values that come from this hash function are between 0 and 1. And I'm going to maintain, this is an ordered list. So my first set of samples, I get 10 samples, and they're randomly sort of distributed between 0 and 1. And I've got 10 samples. So if I look down my list, I can see 2 Ds. I don't know if I can point here. I've got this separation here. I could use that as an estimate because I take 1 over that D, which is 0.19, and I could get, but it was pretty bad. I get only an estimate of 5. I take another separation here between the curb, 0, and this number, and I get 125. So that has a huge variance. It's pretty noisy. So what else can we do here? So we could try what's called K minimum values. And so I'm going to lock one end of my distance at the curb, which is 0. And then I'm going to take 3 values. So I'm going to choose some value we call K, which is a constant. I'm going to call it 3. And I'm going to say, okay, I'm going to take the smallest 3 values in this whole list. The others become dimmed, so I can throw them away. I don't need them anymore. Okay, so then I take the value of the third one, which is my kth value, and that is, by the way, its value is also its distance from the curb, from 0. And so then I do this one little adjustment. I take k minus 1, which becomes 2, and then divide it by this value. And this, when I do that, I get an estimate of 10.26. Now, part of that was luck. But it turns out it's a much better estimate. Okay. So now I have a couple more things I have to do. So if I get a new hash value that's greater than this kth minimum value, I throw it out. Automatically reject it. Don't even look at it more. Also, I reject any duplicates. So if any item that appears in the stream is already one of these K minimum values, I also reject it. So if a value comes in that is not a duplicate and not greater than that, then I insert it in order in this little list, bump the top value, and replace my kth minimum value with the one that was just before it. Okay, so far? Okay, this is called the K minimum value sketch, or the KMV sketch, for counting unique values. And it turns out it has some other amazing properties in terms of its accuracy. So you go through a couple pages of calculus, so I won't bore you with that here. And it turns out that your what's called the standard error, okay, of this estimator is a function of a constant, 1 over the square root of k minus 2. K is a constant, remember, you chose it. So that means the error is, the relative standard error is constant whether you're measuring values in the thousands or trillions. Okay? This is how it actually looks. So this was chosen. Now we choose larger values of k than 3. So here I'm going to choose 4k, or 4 times 1024, 4096 values in this sketch. And you can see that as long as I've only entered in less than 4096 values, it already does deduping. Basically, it's like a hash table, so it does deduping. So as long as I haven't exceeded 4096, it's perfectly accurate. This is the error axis here, and 0 error means it's absolutely accurate. So for small counts, perfectly accurate. As soon as it exceeds this limit k, which you've chosen, then you can see that it begins to err a little bit in its estimate. Sometimes it's an overshoot, it overestimates, and sometimes it underestimates. And these are quantiles. So 5% of this is like the 5th percentile, and that's the 95th percentile. Now, if you could slice this vertically and do sort of a 3D slice, it would look something like this. And notice that it has a very bell shape here on the cross section. So what you're really looking at is looking top down on a surface whose cross section looks very Gaussian, and it looks very much like this. Okay? That means it's very predictable error. In fact, you can see how these flatten out, and those stay flat into the trillions. Okay? So this is a very powerful concept here, because what I've got on the x-axis is my counts all the way up to 1 million here, and it stays perfectly the same accuracy. So you can depend on that. Here's another one where I've used real data. This first one here was synthetic data, but now I've got real data. This had 5.2 terabytes, about 20 billion events, and we produced about 5 or 10 million sketches. And you can see how the data clusters. As soon as it goes into what we call estimation mode, it clusters right there in the center, and it's very sparse at the edges. And so if you actually do a cross-section and measure that error, you can see it's well within your error bounds. You can rely on this error distribution so well that we have found bugs in what we call our ground truth measurements that were supposedly done, exactly, and oftentimes took days to compute. We've found errors in that logic because this is so reliable. It has a little error on it, but it's a very well predicted, very predictable Gaussian error curve because it's white noise. So we can actually take advantage of that. How fast is this? Pretty fast. In updating items into this sketch, this middle line across here is, I'm sorry, I have to show it up here. That's about 25 nanoseconds, and that's 40 million updates per second, faster than most of the other processes you're probably using. But in fact, as you go towards the end out here, it gets even faster because your value of the kth minimum has gone smaller and smaller, and you're down here around 8 nanoseconds, which means it's over 100 million updates per second. That's pretty fast. So you can definitely put this in a real-time stream. The spiky one is where it's doing internal resizing, and this is another option where you can have it not do resizing, and it's still pretty fast. Okay, now, the other thing we can do with these is we can merge them together, and that's where we get the additivity quality. So you can build a sketch of users from US, a sketch of users in US, and you can merge them, form the union, or you can do the intersection of those two sketches like that. Okay, and it will tell you an estimate of what those set operations are. And this shows the unioning process of about 14.5 million sketches per second per thread of your operating system. Okay, so we've pushed this technology farther at Yahoo, and we've developed basically a library and a framework around theta sketches where we have about 20 some odd different variants of these sketches for different kinds of purposes, whether it's on heap, off heap, the direct, indirect. So there's a lot of different ways to optimize these sketches. These are examples of the kinds of queries we can do internally. You might say, I want a sketch of my sports population, a sketch of my finance population, and then I want to find out the users that have visited both. That's an intersection. Or I can say, how many non-US users visited yahoo.com in January that also visited in February? So by getting the non-US, I do a basic intersection between January and February and do not those in the US. So this allows you to do powerful analytics on unique usage quantities in real time. Now, I'd be remiss if I didn't talk about the hyperlog sketch. This has gotten a lot of popularity. It was invented by Philippe Flageolet, French mathematician, who really is the one that launched this whole science of sketching. In about 2008, it was a theoretical paper, and has exploded in use since. The log sketch is it's a lot more complicated to explain, but it is the smallest space sketch for a given counting accuracy. It's about eight times smaller than the sketch I just explained to you. It's outstanding for simple counting and simple merging. We have a version of it. We have 2 versions of it in our library. But it's unsuitable for set intersection or difference because the errors are so large. It doesn't have the right kind of data structure for that. And it has a couple of restrictions. Generally, it relies on exclude approach, which has huge error, and all the targets must be the same size, which is not a restriction on the KMV sketches. To give you a sense of how we have used this at Yahoo, here is sort of a sketch of a Hadoop grid that is doing back-end processing using sketches. And you can see how you have front-end data being sketched here, and then it goes through a unioning process. Then, for instance, we might do sketch on a daily basis, and then combine the days into, a sketch on an hourly basis, and then combine the hours into days. Then you combine 7 days into a week. So you get different time-based views of your data here. That's all extremely fast. And then we'll have some sort of query engine for a reporting engine on the front end that takes sketches from the grid, puts them in memory, and then does, on a query time basis, pulls together the sketches and does the union or set operations that it needs to produce the results for the query. We have this running today. Now, one of the big advantages, again, of this is a vast simplification of your pipeline architectures. In the process, the system that preceded this, that did everything brute force, this data is huge now, so probably 50 to 100 terabytes a day. So it had something like 15,000 process steps and hundreds of pig scripts running on Hadoop. This process, when we re-engineered it using sketching, it reduced it to 50 process steps and 6 pig scripts. So you can, and of course it was operating faster, much faster on much fewer resources. So it saves energy, if nothing else. Now, the other thing I think we wanted to announce is that we're going to be open sourcing this library. It's written in Java. We also have pig scripts for Hadoop. Now, so if you exclude the pig scripts, it has no external dependencies. So you can wrap this library directly into your systems and leverage it just like we are. Thank you. Want to say anything else? Open for questions?
Yeah, and one caveat on that. We are in conversations to open source this. It's not available yet, and there's no GitHub URL or anything yet, but we are very hopeful that we will eventually be able to open this up. Anyway.
Yeah. Any questions? Yes.
The question is, are we using MapReduce 2 or Spark? And the grid side of the processing is just, it's MapReduce. Some of it's on Tez, some of it's on good old-fashioned MapReduce. And the output of that then generally gets loaded into Druid, and Druid does all of the actual serving to end users.
Yeah, that's one of the things we haven't decided yet. But look for announcements from Yahoo on sketches and sketching. Yeah. Any other questions? Yes.
If I understood this right, your hash function is what makes the signal look like white noise.
Yes.
Right? Any challenges around finding a hash function that doesn't do that or does that?
I would say you need a decent one. What I did is wrote a version of Austin Appleby's Murmur hash 3, which is in, it's on the public website. He wrote it in C, and I did some enhancements to it and wrote it in Java, but it's that will be part of the library. And one caution about hashing things, because now all of your identifiers, whatever they are originally, strings or whatever, become a hash value. And once you start collecting history in these sketches, you don't want to be changing your hash function, your hash key, for instance, or your hash seed, right? Because then all of a sudden you've lost everything. So that's the only precaution. Start with a good, I'd recommend you, if you're going to use this library, just use the one that the hash function that comes with it. It generates a 128-bit hash. So any other questions? So everybody can go home and explain to their kids what sketches is.
Thank you.
Thank you.